Greetings, and thank you for the curiosity that keeps you watching our materials. Having reached around the Middle Ages with our historic presentations, we decided to pay close attention to the Italian researchers and scholars. Not only did they contribute immensely to the progress of arts, crafts, and science, especially during the Renaissance period, but they are also home to some of the most interesting, non-violent, purely intellectual duels mankind has seen so far. In a world full of so much anger and bloodshed that's nothing like the civilized society most of us dreamed of, we thought we should tell you about the days when the brightest minds fought each other with equations. Now, in order to give the episode a clear direction, we will be focusing on the story of polynomial equations. And we can start straight away with a book recommendation that traces the subject from the Middle Ages to the 1800s and even to present days. It was written by the Bucharest-born astrophysicist and popular science writer Mario Livio, and it's titled The Equation That Could Not Be Solved. Explanations about the title will be given along the unfolding of the current episode. We have showed you that ever since the dawn of writing, in the Babylonian, Egyptian, then Greek civilizations, people have used equations for multiple purposes. Now, if you're wondering about the etymology of the term equation, it's not hard to guess it. It comes from the Latin word equare, meaning to make equal, and it is generally a relation between two expressions, one called the left-hand side and the other the right-hand side. In principle, even a straight equality such as x equals 3 can be called an equation, but in most cases, equare is focused on making the sides equal. That is, finding some conditions or some unknown quantities that make such that the sides become equal, whereas in x equals 3, there's nothing left to find. While all types of equations have fascinating stories to tell, which we will hopefully cover in future episodes, the focus now will be on algebraic and polynomial equations. One can even argue that the basic algebraic operations appear more or less naturally in the history of mankind, unlike the more sophisticated trigonometric functions, differentials, integrals, etc. Hence, algebraic equations were the first to appear in close relation to everyday life.
But before proceeding, let us give a brief but rigorous presentation of what polynomials in one indeterminate are and how they give rise to polynomial equations. From a scholastic perspective, polynomials appear in the last year of high school in a more general form, but probably they start to show up already since the 9th degree. Generally, an expression such as this one, where the symbols AI often stand for real numbers, is called a real polynomial in one indeterminate, x. Not real in the sense that we may have fake polynomials, but in the sense that it has coefficients which are real numbers. It is an expression which consists only of natural powers of x, including 0, and coefficients, which can be any number, including 0. It involves only addition, subtraction, and multiplication. The highest power of the indeterminate x is called the degree of the polynomial. So, for example, this is a polynomial of degree 3. This one is a polynomial of degree 100, and this is a polynomial of degree 0. Note that in order to have a polynomial, one must use natural powers of x, hence 1 over x is not allowed, nor is square root of x. With this notion at hand, one calls a polynomial equation an expression which imposes equality of two polynomials. Therefore, some examples of polynomial equations are these ones. Notice that one can always move all the terms to one side and leave only 0 on the other side, which is why in most books polynomial equations have the third form from our example, namely some polynomial equal to 0.
A quick detour. Have you wondered why the unknown in equations is usually denoted by x regardless of the type of the equation? Here's the reason. As we mentioned in many of our previous episodes, one of the most important figures in the history of algebra is Muhammad al-Khwarizmi, whose book titled Al-Jabr Kitab even gives the name to the whole field. Now, al-Khwarizmi used the word al-shay to denote the unknown in his equations. Al-shay literally means something, in the sense of some indeterminate value. Before the 16th century, most equations and solutions were more or less expressed in a prosaic form. Hence, an equation such as this one was told something like a square is added to 3 lengths and we get a unity. The Spanish were among the first Europeans to translate Al-Khwarizmi's book, and since there's no sh sound in Spanish, they replaced it with their closest variant, h. This in turn became he in Greek, which is this letter. Later, when the Latin language became most commonly used for science, the he became its closest looking relative in the Latin alphabet, which is X. The first mathematicians to actually introduce the notation we use today were the French René Descartes and François Viète around the 1650s. In fact, they first worked on using the symbols we have today for powers of the indeterminate, but the complete form of equations as we know them today appears systematically a bit later. In the case of linear equations, here's a picture of the writing of the equation 14x plus 15 equals 71, in a book by Robert Record of Wales from 1557. Notice how the symbol for the unknown still resembles more or less to a mirrored version of the al-Shai.
Now, it can be easily argued why algebraic and polynomial equations arise naturally. They are probably among the most obvious uses of mathematics in real life. Every time one computes some area, some volume, their budgets, their expenses, and so on, polynomial equations show up. Many formulas in geometry or physics can be expressed as polynomial equations. And when one considers more complex geometric figures or tries to relate, say, a square with a circle of the same area or to inscribe a pyramid in a sphere, quadratic or even cubic equations are used. By the way, the name itself for x squared or x cubed shows this deep root of the use of algebra and geometry. X squared is the area of a square of side x, and x cubed is the volume of a cube of side x. And there is also the name linear equation to mean a first-degree equation, which is coming from the fact that when drawing the points that are in a linear correspondence, we get a straight line. Perhaps entities living in higher dimensional universes also have names for x to the fourth or x to the fifth as some kind of hypervolumes of hypercubes. Babylonians, Egyptians, Chinese people had means of solving first-degree equations in a more or less general way, but it wasn't until Al-Khwarizmi that an actual algorithm appeared for a step-by-step solution. Nevertheless, his predecessors from the 5th millennium BC did more than a great job with these equations. Even more, as you may remember, Chinese people were able to solve simultaneous linear equations involving even negative quantities. The same ancient people made some remarkable progresses toward a general solution of the quadratic equation. There was of course no formula with the discriminant as we use it today, but in some Babylonian tablets one can see a quite detailed analysis of particular cases of the well-known quadratic equation. They were followed by the Chinese with their 9 chapters of mathematical art, and by the Greeks, most notably with Euclid in the 3rd century BC, who used geometric methods, and Diophantus in the 3rd century AC, who instead used arithmetic and algebraic methods. The Indian Brahmagupta in the 7th century AD found a way of expressing the solution with a formula that is quite similar to the one that we use today for the general case. By the way, by a general solution, we mean one that would work for all equations regardless of their coefficients. Best way of expressing it is by a formula depending only on the coefficients, an expression like this one, in which one only needs to replace the actual coefficients a, b, and c, and that works for all quadratic equations. Going back to the general solution of the quadratic formula, it first appeared in a more or less prosaic form in a book by the Flemish mathematician Simon Stevin in 1594, but the actual symbolic form we use today can be found in Descartes' La Géométrie from 1637.
Next stop, the third-degree or cubic equations, which as we mentioned were also rooted in geometry, that is, in practical needs of computing volumes. Again, the Babylonians, Egyptians, Chinese, Greeks, and Indians tried solving them, but they only managed to get results for particular cases. The general formula, which exists and is not very different from the quadratic one, but it is not taught in schools, is also due to Descartes and Viète, with some other mathematicians such as the Italian Girolamo Cardano and Joseph-Louis Lagrange making important contributions. The quartic, or the fourth-degree equation, was tackled next, and most of the progress was also made in Italy, but in a rather recurrent manner. That is, Lodovico Ferrari, the mathematician credited to having found the general formula around 1540, did not publish his work, one of the reasons being that it relied on the complete solution of the cubic, which in turn was not public and not available to him. There is also another reason for his secrecy, and we will detail it in a bit. Then, the struggle for the quintic, and why not equations of any degree? Since we intend to dedicate a separate episode to the mathematicians around the solution and their efforts, we will be brief here. There was no obvious reason why, having solved quadratic, cubic, and quartic equations, one cannot solve quintics. So there were efforts from many illustrious mathematicians throughout the centuries, and they managed to solve particular cases, but no general solution. There was no geometric interpretation available given the high dimension, so it had to be purely algebraic. The solution could not have been more staggering. In 1832, after his death in a duel at the age of 20, the world found that the French mathematician Évariste Galois proved the unthinkable. The quintic cannot be solved. More precisely, Galois showed that all algebraic equations starting with degree 5 cannot be solved internally, that is, using algebraic methods. His proof also brought into existence a branch of algebra now called Galois theory and showed an immensely important application of the newborn group theory. Some credit is also due to the Norwegian mathematician Niels Henrik Abel, who before his death at only 26 years of age in 1829, tackled the problem in an important but not decisive way. His use of abstract algebra and group theory is what we honor when we call a structure which has an operation that is commutative, as is the case of addition since x plus y equals y plus x, and multiplication since x times y equals y times x, abelian.
But let us come back to Italian Renaissance. At that time, the quest for solutions of algebraic equations in Italy was characterized by very high secrecy and gave rise to amazing stories. This was probably due to the practice of mathematicians of publicly challenging one another. Apart from money, the loser may often lose the protection of the nobles of the time, or even the position at the university. So, it was very important to always keep the greatest results up one's sleeve. In fact, there was a strong competition among mathematicians, a competition which was not unusual to go public. But let us proceed step by step. Scipione del Ferro was among the first to completely solve a particular case of the cubic equation, namely this one. This was incredibly challenging, since Del Ferro did not know how to use negative number in equation, for example. However, he was particularly skilled in using cubic roots. For example, he contributed in rationalizing fractions with denominators of this form. Not much is known about his life, and there is no surviving original work from Del Ferro, but it is thought that he studied at the University of Bologna, his hometown, where he might have met Luca Pacioli, whom we already talked about and who is considered the creator of the double-entry bookkeeping method for accounting in Europe. What is known is that Del Ferro had a not particularly brilliant student, Antonio Maria del Fiore, but even to him he did not confide about his work on the cubic, not until briefly before his death. A second key figure of the time was the Venetian Niccolò Tartaglia. Most of his mathematical education was self-taught, and he also wrote extensively on physics. In his Nova Scientia, published in 1537, he treats problems of falling bodies, ballistics, and even sinking ships, largely influencing Galileo's work. But it is for his role in the discovery of the formula for the solutions of the cubic equation that we are meeting him today. In Tartaglia's book Quesiti, which was published in 1546, it is written that around 1530, a professor from the University of Bologna called Swan da Coi, also known as Giovanni del Colle, proposed to Tartaglia two cubic equations to solve. In modern notation, they are these. More or less around the same period, in 1535, Tartaglia was even challenged by Del Fiore to a cartello di matematica di sfida, with a monetary reward. Both had to contribute some money and give each other equations to solve within 30 days. The one solving more equation would win all the money. Del Fiore, of course, gave to Tartaglia equations of this form, which he knew how to solve thanks to his master Del Ferro, whereas Tartaglia proposed equations of this form. It seems that it was around that period that Tartaglia discovered again, independently, a solution for the cubic equation. By the way, it also seemed that his formula was probably more general than Del Ferro's one, as he defeated Del Fiore. Anyway, it is exactly around the formula discovered by Tartaglia that a huge controversy arose, especially with the fellow mathematician Gerolamo Cardano. In 1545, Cardano published his Ars Magna, also called Ars Magna in English, an influential treatise of algebra. Therein, he used systematically and rigorously negative numbers in equations. He also acknowledged the existence of imaginary numbers and made significant progresses toward the solution of cubic and quartic equations. However, when Cardano wrote in his Ars Magna about the solution of the cubic, he duly credited Scipione del Ferro for the solution of the cubic and Cardano's student Lodovico Ferrari for the solution of the quartic. But for a special case of the cubic, namely this one, which Cardano included in his book, Tartaglia claimed that it was him who showed the initial solution to Cardano, making even him swear to not reveal it. Probably what happened was that Cardano discovered Del Ferro's original solution, which was older than Tartaglia's one, and with Ferrari he managed to extend it to the general case, thus feeling free of publishing the result in spite of the promise made to Tartaglia. In any case, the dispute between Cardano and Tartaglia sparked some literal duels for solving cubic and quartic equations. It seems that Tartaglia, with offensive words towards Cardano, denounced the violation of the oath made to him. As a consequence, Cardano's student Lodovico Ferrari launched 6 challenges to Tartaglia within 2 years, and finally he defeated him in an event which was a hard blow to Tartaglia's prestige and finances.
A more or less similar duel was happening in France. In 1596, the Dutch mathematician, astronomer, and professor of medicine Adriaan van Romen proposed to all of Europe an equation of degree 45, which is this one. The Dutch ambassador in France teased the King Henry IV that there was no Frenchman who could solve the equation. The king showed the equation to Viète, and after thinking for a couple of minutes, he found the solution using a trigonometric trick. He noticed that the equation can be rewritten in terms of sin of x and sin of x over 45, which leads to an elegant solution that we don't detail here but link in the references. What's also striking is that the equation had 22 solutions, all of which were found by Viète until the next day. In response, Viète sent back to Van Romen a problem of geometry, dating back to Apollonius of Perga, which was to be solved using a ruler and compass. The problem was to find a circle that is simultaneously tangent to 3 given circles, like so. Van Romen did solve the problem, but he cheated in that he used a hyperbola, like in this image. Viète did not accept the solution, but nevertheless it led to important expansions, most notably by Sir Isaac Newton in 1687. Apollonius' problem was since generalized and led to fractal images such as this one. You may have noticed that there are many prominent researchers that we have not mentioned. Perhaps the most important examples are Galileo Galilei and Leonardo da Vinci. Their popularity, as well as the immensity of their works, which can hardly ever be overstated, are the arguments for which we decided to skip them. That is, instead of just briefly fitting them in a less than 5-minute talk, we decided to postpone their presentation for some special episodes or even full courses. That is not to say that the contributions of the scholars that we mentioned here are easy to blitz through, but we did try our best to fit them all in a hopefully coherent exposition. Finally, as usual, stay curious, ask questions, and exercise your mind, even in mathematical duels.